So, in the last lecture we were examining the flow in a pipe due to a pressure difference across the ends of the pipe under steady state. Okay. We have a pipe of radius r, okay, across which we have applied a pressure difference delta P, and we wanted to determine how the flow rate is related to the pressure difference. The momentum balance equation for this at steady state, okay, in the absence of any forces, was minus dP by dx plus mu by r d by dr of r dvx by dr is equal to 0. Okay. And dP by dr was equal to 0. P was not a function of r, it is only a function of x, and dP by dx is equal to a constant. We showed that by taking another derivative of this momentum equation and showing that d square p by dx square is equal to 0 in this case. Therefore, p is only a function of x because it is at steady state. Vx is independent of x for a fully developed and steady. Okay. Okay, and steady. Okay, it is fully developed and steady. Okay. And since dP by dx is a constant, I can take it to the other side and integrate it. What we had actually done was to integrate the equation in terms of the shear stress. Okay. And the shear stress, the boundary conditions were that at r is equal to r, Vx is equal to 0, and at r is equal to 0, we had the symmetry condition. Okay. Tau xr is equal to 0 or dVx by dr is equal to 0 from Newton's law of viscosity. Okay. That is because we know that at the center the velocity profile has to go through an extremum. Okay. If it does not go through, have 0 slope at the center, then the slope will not be continuous as you approach the axis from different directions for an axisymmetric flow, where the velocity does not depend upon the angle around the center. It depends only on the distance from the axis. It does not depend upon the angle around the axis. Okay. So, in that case you can get a unique solution for the slope of the velocity only if it is 0 at the center. So, these were the two conditions, and we had solved this, okay, to get Vx is equal to minus 1 by 4 mu dP by dx, okay, into r square minus r square. Note that dP by dx is negative because as you go downstream the pressure has to decrease, and therefore the change in pressure divided by the distance travelled will be a negative number if the velocity is positive. So, the fluid flows from higher pressure to lower pressure. Okay. And we had also written this as this is equal to V max, maximum velocity at the center, into 1 minus r square by r square. Okay. The shear stress tau xr was equal to, okay, mu dVx by dr is equal to minus 2 V max r by r square. Okay. That was equal to the shear stress. Okay. and this can be written in terms of the pressure gradient as equal to minus dP by dx into R by 2. Okay. And the wall shear stress was minus dP by dx into R by 2. Okay. I should note that this is the stress that is exerted by the fluid on the wall. Okay. So, it is in the plus x direction. The stress that I had calculated in the last lecture was exerted by the wall on the fluid, and that was in the minus x direction. Okay. Okay. So, this is the stress in the minus x direction that is exerted by the wall on the fluid. Okay. And if I write this in terms of the pressure, I will get just a positive sign here. Okay. So, that is the wall shear stress, which is negative. Okay. It is defined to be negative. Okay. Apart from this, we had calculated the flow rate. Okay. We had calculated the flow rate V dot is equal to integral 2 pi r dr times Vx. 2 pi r dr is the differential cross sectional area times the velocity gives you the volumetric flow rate, the flow rate per unit, the volume transported across that cross section per unit time. This is integrated from 0 to r. Okay. And that was equal to minus, let me write this as r power 4 by 8 mu into minus dP by dx. Okay. And the average velocity is equal to the volumetric flow rate divided by the cross sectional area pi r square. Okay. And this was equal to r square by 8 mu into minus dP by dx. Okay. And in this equation we had V max was equal to r square by 4 mu into minus dP by dx. Okay. Therefore, we get that the average velocity 2 times the average velocity is equal to V max. So, those were the relations that we had derived, quite straightforward in the last lecture, and the final relation was the friction factor correlation. Okay. The friction factor is equal to the wall shear stress by rho V average square by 2, the fanning friction factor, okay, the wall shear stress by rho V average square by 2. For the wall shear stress, I can substitute this. Okay. The magnitude of the wall shear stress is equal to minus dP by dx into r by 2. Okay. And I'll substitute, I'll express in terms of this expression only for one of the V average, because I know that the other one will go into the Reynolds number. So, I get rho V average by 2 into the average velocity, which is equal to minus dP by dx into r square by 8 mu. Okay. That is substituted from here. Okay. And this negative of dP dx cancels out on the numerator and the denominator. This cancels out, and ultimately I will get this is equal to mu by rho V average, okay, times r, and this is a factor of 8 here, okay, if you do the algebra, okay, and this is equal to 16 by Re, okay, where Re is equal to rho V average d by mu. The Reynolds number is defined in terms of the diameter of the tube, which is 2 times the radius. Okay. Therefore, if I substitute for this as d by 2 in the denominator here, I will get 16 by Re is the Reynolds number. 16 by Re is the friction factor. Okay. So, that gives us the relation between the friction factor and the Reynolds number. Before we go on to an example, I would just like to briefly explain one other issue about this pressure gradient and the viscous stresses. So, for this particular steady state configuration we had got. Okay. So, let us just consider an unsteady state, rho times partial V x by partial t is equal to minus partial p by partial x plus 1 by r d by dr of r tau x r expressed in terms of the shear stress plus a force F x, okay. A body force density, force per unit volume. Okay. If dP by dx is a constant, okay, if dP by dx is a constant and the force is also a constant, you can see that both of these are constants. Okay. And because of that the two can actually be combined. Okay. The effect of a pressure gradient is identical to the effect of a body force in the x direction. Okay. So, the two can be combined. In fact, you can make a stronger correlation. Okay. If the force, okay, if the force can be expressed as minus the gradient of a potential energy, okay, if the force can be expressed as minus of the gradient of the potential energy, right, conservative force, okay, a conservative force can be expressed as the gradient of the potential energy. Dissipative forces cannot be expressed as that. Okay. So, if the force can be expressed as minus the gradient of the potential energy, where u is some potential energy, okay, then in this equation I can substitute rho times partial V x by partial t is equal to minus partial p by partial x plus 1 by r d by dr of r tau x r minus partial u by partial x. Okay. And if I define a new pressure as P plus u, okay, this just becomes equal to rho times partial V x by partial t is equal to minus partial of P plus u. Okay. This is just P prime by partial x plus 1 by r d by dr of r tau x r. Okay. So, having an additional body force which is conservative, which can be expressed as the gradient of an energy, right, then that force can be combined into the definition of the pressure itself. Okay. That force can be combined into the definition of the pressure itself. Okay. So, for example, if my force F x is equal to minus rho g, okay, okay, so that is that if I have, for example, a pipe which is slanted in, okay, okay, or okay, and therefore, the force along this x direction will be g x. Okay. So, if it's easier to take a vertical pipe in order to make the case. Okay. Okay. So, if you have a vertical pipe in which this is the z direction, okay, and this is the direction of gravity, okay, I am sorry, this is the x direction, in which the gravitational force is acting along the axial direction, along the axial x direction, okay, in the minus x direction. Okay. Gravitational force is acting downwards, x is the coordinate in the upward direction. Okay. So, if you have this kind of a force, right, then you know that the energy is equal to rho g x times x. Okay. Okay, the energy is equal to rho g x times x, and therefore, P prime is equal to P plus rho g x x. Okay. The pressure plus the potential energy, okay, is P prime, and it is this gradient that is specified. The velocity profile depends upon partial P prime by partial x instead of partial P by partial x that I had over here. Okay. Instead of the partial P by partial x, I just have to substitute partial B by partial x plus rho g x or minus rho g x depending upon the sign. Okay. So, because of that, a pressure force can be quite easily combined with a potential energy term due to, for example, hydrostatic head, to get a definition for P prime which combines both of these. Okay. And this has to be used in the momentum conservation equation or in the expression for the friction factor and so on. Okay. So the effect of having a body force is similar to the effect of having a pressure gradient. Okay. If that force can be written as the gradient of a potential. So, you just add the potential to the pressure, okay, to the fluid pressure. Okay. So, let us solve an example, okay, in order to find out how to use this friction factor correlation for actually finding out the change in height of a column of fluid, for example. So, I have two tanks. Okay, with a pipe connecting the two. Okay. I will call this as tank A, this as tank B. Okay. There is a difference in the water level or the fluid level between these two tanks, and at time t is equal to 0 you open the valve between these two, and you want to find out what is the time it takes for the fluid to flow from one tank to the other. Okay. So, that is the problem. The two are connected by a pipe, and that pipe has okay, a length of 5 meters is the length, okay, and the diameter of the pipe is 1 centimeter. Okay. The area of tank, the first tank is area of tank A. Okay. Area of tank A is equal to 1 meter square, area of tank B is equal to 2 meters square. Okay. Initial height h in tank A is equal to 3 meters and h in tank B is equal to 0. Okay. And at time is equal to, at t is equal to 0, the valve between the tanks is opened. Okay. How does the height vary with time? Okay. How does HA and HB vary with time? Okay. So, that is what we are trying to solve for. Okay. And we will assume that this volume in the pipe is much smaller than the volume of the tanks. So, it can be neglected in comparison to the volume of the two tanks. Okay. So, how do we solve this? First is we have to use volumetric balances in order to find out the relationship between the height in tank A and the height in tank B, okay, at any time. Okay. After the valve is opened, we have to use balances to find out the relationship between the height in tank A and the height in tank B. Okay. The initial volume of fluid is the area of tank A times the height of tank A initially. HA naught is the initial height in tank A, that times the area is the total volume. Okay. This has to be the same as the volume at any point in time, okay, which is the area of A into HA plus area of B into HB. Okay. So, substituting these values, 1 meter square into 3 meters is equal to 1 meter square into HA plus 2 meter square into HB. Okay. Therefore, this gives me HB is equal to 3 minus, sorry, 3 meters minus HA by 2, okay, is equal to 3 meters minus HA by 2. What is the difference in the height between the two tanks? Okay. HA minus HB is equal to HA minus 3 meters minus HA by 2, okay, is equal to 3 by 2, okay, into HA minus 1 meter. Okay. So, 3 by 2 into HA minus 1 meter is the difference in the heights, okay, of the two tanks. And this 3 by 2 into HA minus 1 meter, you can see that when HA is equal to 1 meter, HB is also equal to 1 meter. Initial height was 3 meters and cross sectional area was 1 meter square. Okay. In the final state, HA has to be equal to HB. The initial volume was 3 meters square. The final volume, if the height HA and HB are 1 meter, the volume in the left tank is 1 meter square into 1 meter. On the right tank, it is 1 meter square, 2 meters square times 1 meter. Therefore, the final volume is also equal to 3 meters square, cubed. Okay. So, the initial volume is 3 meter cubed because the initial height is 3 meters, cross sectional area is 1 meter square. In the final state, both heights are equal to 1 meter. The cross sectional areas are 1 meter square and 2 meter square respectively. Therefore, the total volume is 3 meter square. So, this final height HA is equal to 1 meter satisfies the total volume conservation condition. Okay. So, now we know that the difference in heights results in a pressure difference across the two ends of the pipe. Okay. The difference in height results in a pressure difference across the two ends of the pipe. Okay. Delta P is equal to rho G into HA minus HB. Okay. And we also know that for the pipe, the pressure difference, pressure gradient is related to the volumetric flow rate. Okay. Is equal to V dot by the relation 8 mu V dot by pi r power 4. Okay. That was the relation between the pressure gradient and the volumetric flow rate, if you recall. Okay. We had calculated this here. dP by dx here is equal to V dot is equal to 8 pi r power 4 by 8 mu into dP by dx. Okay. Which means that dP by dx is equal to 8 mu V dot by pi r power 4, which is what I have used here. Okay. So, this is the difference in pressure between A and B. Okay. Delta P by L is equal to 8 mu V dot by pi r power 4, and this is also equal to, okay, rho G into HA minus HB by L, okay, from this equation. Okay. Now, we have to relate V dot to the change in height. Okay. We know that V dot, okay, when fluid flows from the left to the right tank, okay, when fluid flows from the left to the right tank, okay, there is going to be a decrease in height of the left tank. Okay. Therefore, V dot is equal to minus the area of tank A times dH by dt, okay, is equal to minus of the area of tank A into dH by dt. Okay. So, that is the volumetric flow rate. So, this gives me minus A dH by dt, okay, this is HA, okay, the height of tank A, because when when fluid goes from the left to the right tank, the height of tank A reduces. Therefore, V dot is equal to minus the area of tank A times dH by dt, okay, into 8 mu V dot by pi r power 4 is equal to rho G into HA minus HB by L. Okay. And for HA minus HB, I can substitute from here. Okay. This is equal to 3 by 2 rho G into HA minus 1 by L. Okay. And with this, if I equate this term with this term, okay, I will get dHA by dt is equal to minus, okay, 3 rho G into HA minus 1 by 2L into pi r power 4 by 8 mu. I am sorry, there is no V dot here. V dot is already, V dot is the volumetric flow rate is this one. Okay. This is the volumetric flow rate times 8 mu by pi r power 4. Okay. So, there is no V dot here. Okay. So, this is equal to minus 3 pi rho G r power 4 by 16 mu A L. Okay. There should be a factor of the area here in the denominator, because I have divided by the area over here. Okay. This whole thing into HA minus 1. Okay. And I can write this as minus HA minus 1 by the characteristic time Tc, okay, where Tc is equal to 16 mu AAL by 3 pi rho G r power 4. I will leave it as an exercise for you to verify that this actually has the same dimension as time. Okay. So, in the original problem I had these parameters, and in addition if I take the density rho is equal to 10 power 3 kg per meter cubed and mu is equal to 10 power minus 2 kg per meter per second. Okay, this is a fluid which has 10 times the viscosity of water. Okay, so, that is what is specified in the problem. And on that basis I substitute in here, I will find that this Tc is equal to 16 into 10 power minus 2 kg per meter per second into the area of tank A is 1 meter square, length is 5 meters as I had said earlier, divided by 3 into pi into 10 power 3 kg per meter cubed into 10 meter square per second into the diameter is 1 centimeter, okay, that is 0.01 meter, okay, whole power 4. And this thing turns out to be 1.36 into 10 power 4 seconds. Okay. So, that gives us the equation for the change in height with respect to time. Okay. This equation dHA by dt. Okay. You can solve this equation. I will leave it as an exercise for you. You will find that HA minus 1 meter, okay. I should put 1 meter here, there is a dimension, okay, by HA naught, the initial height minus 1 meter is equal to e power minus t by Tc. Okay. That is the final equation that you will get if you solve this equation. Okay. And you can easily verify that at t is equal to 0, HA is equal to HA naught. Okay. So, that is the final solution of the equation. Note that we have used this relation. note that we have used this relation. Okay. This is valid only for a laminar flow. Laminar flow only for Reynolds number less than 2100. So, after we solve the problem, we have to verify that this is correct. The flow is laminar and the Reynolds number is less than 2100. Okay. So, that I will continue in the next lecture. I will verify that the flow is laminar and the Reynolds number is less than 2100, and therefore, this solution is valid. In case you do not get the flow to be laminar, then you have to change the solution procedure, assume a turbulent flow and then calculate, use the friction factor for that turbulent flow. Okay. This is only for a laminar flow. 16 by Re is the friction factor relation implicit in this calculation. I will continue that in the next lecture before I go on to another example of the pressure of the friction factor for a non-Newtonian fluid. I will continue this in the next lecture. I will see you then.